Okay, so in the last episode, we looked at thermodynamics and movement of thermal energy. But before we move on to actual heating design, we need to take one thing into consideration, particularly when it comes to fabric heat losses, and that is a U value. So what are U values when it comes to fabric heat losses? Well, actually, they are everything. A U value is a fabric's resistance to thermal energy movement. Take my house, for example. It's built using different construction methods and different materials. I have a concrete floor below me. I have plasterboard walls behind me. On the outside wall, we have a timber kit that's insulated with brickwork on the outside. And also we have windows, obviously, as well, so as we can shed some light into the property. Because these are all built using different construction materials, each of them has a different resistance to thermal movement, or U value as we term it. We would get more heat loss through my windows, for example, than we would through the walls that have been insulated. So let's dive into what a U value is and how it plays a part in our heating design. So let's dive more into the world of U values. Now, when it comes to central heating systems in our homes, I'm very much an advocate of the fabric first approach. Now, what do we mean when we talk about fabric first? Well, it's all about the efficiency of our home. In my opinion, it's ever so slightly counterproductive to design our system as accurately as possible and then make efficiency improvements to our home. All of a sudden, our heat pump system would be oversized. So if we can max the efficiency of our home prior to heat pump design, then we'll have a much more successful journey. So ways that we can increase efficiency in the home. Well, when we talk about efficiency, we're really talking about insulation. We're talking about bolstering the thermal resistance of our home. So we could look at cavity wall insulation. If our home does not have an airspace or a cavity in the walls, we could look at external wall insulation. Underfloor insulation, typical loft insulation, simple things like draft proofing to combat ventilation losses from one room to the next, and also glazing upgrades as well, so be that double or triple glazing. When it comes to calculating the fabric heat loss of our dwelling, the energy requirements from a fabric point of view, then ascertaining an accurate U value is absolutely essential. Because as you delve into the realm of fabric heat losses, you are no doubt going to come across this term U value, whether it's digital software or traditional paper-based. Now, these values are frequently linked with the levels of insulation and heat loss capabilities. You might have heard people talk about the lower the U value, the more effective the fabric is, and it's true. So think about it like this. A U value serves as a gauge for how much heat can pass through a particular material, and we measure it in units of watts per square meter Kelvin, and we'll come to Kelvin just shortly. So fabric heat losses are all about thermal conduction. Let's start with how conductive a material actually is. Now, we should know that conduction is heat transfer due to physical contact between two mediums, but how can we actually measure it? Now, this can be a bit alien to get our head round, as thermal conduction defines the proportional relationship between two other properties of a material, basically their conductive relationship. So what we're basically saying is that any given material has a thermal conductivity value, which is a relationship between that material's heat flux and temperature gradient or temperature difference. If you remember back to our video on thermodynamics with the scales tipping, that's all about speed and temperature gradient. So if we look at this example here, we have a property that has a structure which is internal brick here, external brick here. And again, back to our thermodynamic movement, if we have an indoor temperature of, let's say, 21 degrees and an outdoor temperature of -5 degrees, then thermal movement is impossible to resist. It's the basic laws of physics. But what we can do with efficiency levels is try to slow down that migration from indoors to outdoors. So in this instance, adding cavity wall insulation will create a thermal resistance that will slow that movement. We cannot stop heat movement when there is a difference in temperature, but we can slow it down. So the rate at which a building element conducts heat is given by that U value, which is the number of watts of heat that will flow through an area of 1 square metre when subject to a temperature difference of 1 Kelvin. And we term 1 Kelvin as 1 degree. So always remember, if there is an imbalance and we have not achieved equilibrium, there will always be movement of thermal energy, and always from warm to cool. Now, when it comes to ascertaining a U value, look at our example structure here. We have a number of segments to the puzzle. We have segment A, which is the outside surface on the left. B is our first structural member, which in this instance is outside brickwork. We then have an air gap or a cavity, section C. Section D is our internal structural member, which is, in this example, dense concrete block, followed by a layer of insulation, section E, covered by plasterboard internally, section F, and then G is the inside surface. So in essence, in this example, we have got 7 segments to take into consideration. So to ascertain this U value, in general, the most effective way would be to consult with the manufacturer of that building material. They will be able to give you a fully accurate assessment of that thermal conductivity. But failing that, generally the most traditional approach would be utilising the Chartered Institute of Building Service Engineers Guide, or as it's affectionately known, the Domestic Heating Design Guide. Now you can see an example of one of the tables in section 3 from the guide, which gives detail and estimation of U values. So if we take this example, let's say here for example, we have on the outside wall a 19mm render, a covering, be that rough cast, etc. We then have external brickwork, which is 102.5mm in thickness. We then have a cavity wall insulation, which is 2 inches or 50mm in metric terms. Standard arrated block on the internal structure, and then a coating of plaster, which is 13mm in thickness. Now, based on the inner leaf thickness, the thickness of that standard arrated block, if we were 100mm thick, then our U value would be 0.44 watts per meter squared per degree. But if the inside leaf was slightly thicker and an additional 25mm, that would drop our U value by 0.03. So again, it goes back to the lower the U value, the more effective the structure is at withholding that heat transfer. But if we don't know the U value or cannot gauge an effective estimation from the heating design guide, we may need to calculate it. And to calculate it, we can do it using the examples which are in the domestic heating design guide. And it's calculated by adding up those values from section A through to G in our example. So the actual full calculation is shown here. So the total thermal resistance is the sum of, we term it RSO, added to R1, added to RA, R2, R3, R4, and RSI. And I'll explain exactly what all these are, and we'll look at an example just shortly. So again, if we go back to our example where we have section A, B, C, D, E, F, and G, we can break that down into this calculation. So if R, our target calculation value, is the total thermal resistance, then RSO is the outside surface thermal resistance, R1 is the first element's thermal resistance, then RA is the airspace thermal resistance. R2 would be the second element's thermal resistance. Then R3, if applicable, because it may not be relevant in your example, would be the third element. And then R4, again, if applicable, the fourth element thermal resistance. And then RSI is our internal surface thermal resistance. So this is a table that I have created, which is very similar to that in the domestic heating design guide. So down the left-hand column there, you can see your layers A, B, C, D, E, F, and G, and those are representing the relevant aspects of our calculation. So if we look at element A, which is our outside surface, to ascertain the thermal resistance of section A, we would utilise the table in the Domestic Heating Design Guide, table 3.1. Now, as you can see from the table, the thickness of that element is not applicable, it's the surface. Okay? Thickness is irrelevant in this. So if we go to table 3.1, the outside surface of our exterior wall, which is the first value on the left-hand side there, or our value RSO, is 0.06 of thermal resistance. So that's our first part of the equation, calculated in the end column. No calculations to make, just simply lifting it from the table. Now, R1 is the thermal resistance of our first structural member, section B, and that's outer leaf brickwork. Now, the thickness of that in this example is 102.5, but as you can see in the second column, the thickness column, we need that value in meters. So we take the millimeters and divide it by 1,000 to convert it to meters. Then the thermal conductivity, again, we'll go to the Domestic Heating Design Guide, but this time table 3.12. And for outer leaf brickwork, just at the fourth part down here, we can see that our K factor is 0.840. Now that is the resistance for the thermal conductivity value, I should say, sorry, for our outer leaf brickwork. We would then take the thickness and divide it by that parameter, that 0.84. And that gives us a thermal resistance for section B or R1 of 0.122. RA is our airspace, section C. Now again, the thickness of that is 50 mil, just as an example, which would be 0.05 in meters. Again, using table 3.1, we take the air gap or the cavity, which is the third value, down on the left-hand side, which in this instance would be 0.18. That would be our thermal resistance, because we do not need to calculate the thickness by the resistance or the thermal conductivity, because it is purely airspace. So it's just a constant that we take from the table. Okay, section D is our concrete block. Now our concrete block is 100 millimeters in thickness, which is 0.1 in meters, divide 100 by 1000. Then going back to table 3.12, our dense concrete block has a K factor there of 1.400. We then take the 0.1 meters, divide it by the 1.4, and it gives us a thermal resistance of 0.02. R3 is our section E, our mineral wool insulation. Now again, just as an example, I've said that it's 50 mil in thickness, which would be 0.05 in meters. But to get the thermal conductivity value in watts per meter per degree, this time again, table 3.12, it's shown as 0.042. This table in this section covering insulation, as you can see top left. So we take the 0.05, divide it by the 0.042, which gives us a thermal resistance for the insulation of 1.191. R4 is our plasterboard, section F. So again, just as an example, I've said that the plasterboard is 12 millimeters thick, which is 0.012 in meters. We then use table 3.12 again to get that thermal conductivity, that K factor, and in this instance for plasterboard it is 0.25. We take the 0.012, divide it by the 0.25, and it gives us 0.048 of a thermal resistance. Section G is our inside surface, which again would be from table 3.1. So for the inside surface, our thermal resistance value is 0.12. Again, it's just a surface, so much like the external, we do not need to make any calculations. So the thermal resistance is just a constant lifted from the table, and it is 0.12. So now that we've put some of the parts of the jigsaw together, we can now calculate the total thermal resistance. And to do that, we're going to add all of our figures in the column on the far right. So RSO, R1, RA, R2, 3, 4, and RSI. And that gives me 1.793 of a thermal resistance in meters squared per degree per watt. But to actually calculate the U value, as you can see just here, we take the number 1 and divide it by that total thermal resistance. And that gives us a U value of 0.558 watts per meter squared per degree. Putting all the pieces of the jigsaw together is laborious in some instances, but to get a fully accurate assessment of our fabric heat loss, we must have that U value as accurate as we possibly can. Cool. So hopefully now that you've got a grasp on what a U value actually is, and we've actually looked at calculating that U value as well, we can now adopt that into the next stage, which is our central heating design.